So last lecture, we start to look into the PWM pulse width modulation. So pulse width modulation is we are actually using a variable square wave, like what you see here, in order to apply to the motor. So the motor voltage will no longer become a pure DC, but will be a changing voltage like this. So we can also see that the average voltage to the motor will be just similar using the duty ratio to control them. For instance, the voltage applied to the motor will be just the duty ratio multiplied by the DC voltage supplied to the motor. So the supply voltage will be in such a square way. So the peak voltage applied to the motor will be, say, the source voltage VDC, and then we turn on for dt of the time, and then we turn off. So this period of time will usually equal to 1 minus dt. So the period of this time, this duration, obviously, which is 1 minus dt this time. And the length, the duration of this time, of course, equal to dt. So this ratio will give us the average voltage to the motor. So this is really simple ratio. We are able to obtain the voltage to the motor. So we can change the duty ratio usually from 0 to 1. For instance, the ratio should be between 0 to 1. So that's why the voltage applied to the motor will therefore be between 0 to VDC. To the motor voltage. Sometimes it's a motor voltage. So that's how we can see the voltage we apply to the motor. So next, we need to look into the dynamic operation. That is to say, before we were using a pure DC, apply to it, and then now become a switching waveform. So you see a motor, we do have some winding. The winding will be not only contribute to a resistance, but also contribute to inductance. So both of them will therefore have certain behavior under so-called dynamic performance when applied voltage is not equal to a pure DC, but with a switching waveform. If you do apply a pure DC voltage, then probably the inductor will not respond anything. The inductor will just more look like short circuit. Because we all know that the impedance for inductor equal to, do you remember the impedance for inductor? The impedance for any inductor equal to omega L, right? If a pure DC, then of course there's no impedance. That means the resistance will become 0. So that's why in a pure DC, we don't really need to consider the inductance. So that's why in previous circuitry, we only consider resistor plus the back EMF here. That's RA. Because we are using pure DC voltage to apply to a motor. But now then, when we change into a new condition, so that means we are going to have a resistor together with an inductor, together with a back EMF here. Because the input voltage is no longer a pure DC, become a square wave, because we do have a frequency component here. That will be the input frequency. So that's why once we apply a switching waveform, then the motor itself no longer become pure resistor or back EMF. Then that inductance will therefore behave certain impedance. So we do need to consider its performance. So once we do that, then we need to have another new method to analyze the circuitry. So this method we're going to show you the equivalent circuitry, how they look like. So the summary in this page will be, instead using DC voltage, we're now using a switching waveform. So in the past, the switching waveform, it would be difficult to apply, right? But now the day we use power electronics, we can turn on, turn off quite easily. In the past, our DC voltage, we may use a transformer, we may use potential divider to provide DC voltage. But when we have a more dynamic, higher performance voltage control or motor control, we have difficulty to apply a variable DC voltage. So now then we need to use square wave to apply for this DC voltage. So we call this DC voltage called pulse width modulation, because we are changing the pulse width of the waveform. So that's how you get all the terminology here. So now then the inductance for the armature should be constant. So now then the equivalent circuitry will therefore become a resistor RA plus inductance LA and also the back EMF. So new equation will be like that. So input voltage to the motor equal to the back EMF plus IARA plus LDIDT. So this is the induced voltage from the inductor. This is a very popular equation. I think you all got that. But one thing we can notice from here will be we are using lowercase. So now then I introduce to you the terminology in all the electrical system, the difference between uppercase and lowercase. So how much do you understand about that? What's the difference between uppercase or lowercase in all the electrical system? Yes?
It's variable.
How more do you, but yeah, they're all variable.
No, I mean, they vary. The case ones are good. You don't change.
Yeah, they vary with time. Yeah. So we use, strictly speaking, we say if uppercase is more constant or more look like a DC condition, like battery voltage 1.5 volt, then voltage equal to 1.5, which is uppercase for VDC. And then, but for AC condition, for instance, apply 50 Hertz, 60 Hertz to the system, or 1 megahertz to a system, then we know that the waveform, the voltage are changing. The current will no longer become pure DC, could have some fluctuation, maybe some high frequency ripple. So in this case, when signal are being changed, then we are trying to use the AC instead. Those AC component, we are using lowercase to represent them. So that's why in here we use this lowercase to represent that. Some component we still using uppercase, like the RA. The system is still a fixed parameter. It won't change even though we use AC or switching waveform. The inductance, we are using our meter to measure inductance. So inductance are proportional to N squared, right? And the material. So strictly speaking, we don't change the inductance. So that's why we are using uppercase for the LA. And then you can see the current, because we are using switching waveform applied to here. So the voltage applied here will be this kind of the square wave. So expecting the inductor, we have some changes. Now when we apply positive voltage inductor, the current, this current could be charged up, reduce, increase. We may be in this kind of manner for any inductor. I think you learn electrical circuitry, when you apply square wave to an inductor, the current for inductor will up and down, charge and discharge. Have you seen that? Does it sound familiar? You don't remember? Have you? Okay. Let's go to something more straightforward, simple. Here we got a battery here. And then put an inductor here, right? So when if we turn on, if the voltage here, if the voltage, we turn on the switch, then turn off, turn on. Then of course, because of the LDIDT, that means the current will going to increase, voltage increase in such a way, because that is the voltage input. So that means dI dt equal to V in over L, right? So that means higher the voltage, the quicker you increase current. It's linearly increasing. So that's why I can see that the current, when we turn on, the current will increase. And then when we turn off, then we have problem because we don't allow the turn off without the listening. So we have to add something like a dial to allow it to turn off. So we know the current is going this way. Yeah. So what we need to do will be we adding a dial here. In such a way. If we add a dial in here, even though we turn on, this dial doesn't do anything because it's reverse bias. But when it's turned off, the current here, you need to continue to flow. We cannot stop any other current because magnetic energy storage here, the current will therefore go this way. Like what we are showing you just now. So that's why this current, this first here, second is looking here. So the voltage become off. Then the voltage across the inductor become 0. The voltage becomes 0. Then that means, or that is some reverse current, there's a reverse bias current in here. So the current will be looping here with 0 resistance. Then the current ID change will not change at all in freeway. So in freeway, it will not change at all, right? So next time you turn on, you turn again like that. But actually, down internally still have some kind of the resistance and power losses. So you won't be actually a flat line here, you may decrease due to power losses. So that means what we're going to see here, instead like this, we are going to, instead like this, we're going to see something like that drop and turn on. So we are more look like a kind of triangular way we're going to observe. So that is to say, if we are using this switching circuitry for any inductor, we're expecting the current will increase and decrease in such a way. So that's a typically we can see what happened for inductor operation. But so that's briefly about we can see we do going to see some waveform variation in here. But how the variation, we're going to look into that in more detail in a moment. Okay. So that is to say, when we're using this kind of switching waveform, we're expecting the inductor current will change in some manner. Of course, in here, we don't study in very detail for that kind of what kind of manner it is, but we know that there will be current variation in the system there. Okay. So in here, you can see that when we turn on, that will be positive voltage. And then we're going to see this voltage. For instance, we turn 100 volt. This is 90 volt. Then we got 100 minus 90. We got about 10 volt applied to this R and L circuitry. So let's see the operation. So that means when we turn on, but supposing that the circuitry will be a VDC. Then that means this is the equation, right? So if we would like to get the current variation here, we just rearrange the equation, become this VE minus EA minus I RA, right? Divided by inductor. So that's typical, that's a straightforward. Next, to see this change of the voltage here, the voltage appeared to them would therefore equal, this is the voltage applied across the inductor system. Then that means when we turn on, we have VDC voltage, the source voltage. When turn off, then you can see that we have go back to this circuitry. When turn on, we got VDC voltage. When turn off, the current looping in here becomes 0 volt, right? So turn on equal to VDC, turn off the transistor becomes 0. Okay, so go back to this table here, then we can see that when turn on become VDC, turn off become 0, right? So that's how the voltage across the motor. So that is to say we are going to, so for this motor voltage, we're going to turn on, You got the VDC here, turn off, got 0 volt, and continue to do that. VDC, turn off becomes 0. So that's the voltage we're going to apply to that. And then we can see that the differential equation in here, we can solve the differential equation to obtain the current pattern. In here, we know that the V in voltage, this parameter, will therefore equal to VDC when the transistor is being turned on for duty ratio, for certain percentage of duty ratio, and then you turn off, becomes 0 volt. So that means this expression will become either this one or equal to that one. Do you get that? Very simple substitution. So now then we got two conditions for this equation. One condition will turn on, we are using this parameter. When we turn off the transistor, we are using this parameter. So that's what we're going to see. Now it's getting more complicated, right? But it's something you should be able to handle. So now that when we turn on, why the current increasing? So during that period from 0 to dt, then I call it 0. When I turn on the duty ratio, and the current will be going up. How it go up? You can see that because just now we say the voltage equal VDC. So this is positive. The back EMF should be less than the DC voltage. And then we also some voltage drop here. So that means we're expecting the whole thing here will be positive. If that's a positive, then we're going to see that the IDT will be increasing because that's a positive. So the current will be increasing, and the transistor current also your IDC. What's that second line mean for us? What's that mean?
Second line.
Why? The transistor current equal IDC, what's that mean? Well, obviously, say this label is IDC. The transistor current must equal the IDC because they connect in series. I just try to tell you the current here, the input current will pass through the transistor. So the input current IDC equal to transistor current. If you try to measure the transistor current, you also use IDC. And this current will therefore flow to the armature current. So the IA under the first condition here, they all equal. IA equal to the IDC current. That's all, without any ambiguous. So now then we know when we turn on the transistor, the current will go up. Next will be when we turn off the transistor, the current will looping in the diode. The voltage becomes 0, right? So now then the VDC here will therefore become 0. In this case, that's still negative, no change. So that means the equation is still like that. And then we can see that here, the back EMF, we usually assume them doesn't change that much because rotational speed for the motor. For example, the motor 1000 RPM or a few hundred RPM. Why we can say EA doesn't change? Now you can see I change in EA into uppercase. So EA will be K omega, right? K omega, so omega, but the switching frequency here will be much higher than the rotation speed for the motor. For instance, if the motor is say 1000 RPM, we're talking about every second will be something like really small. So the duration here, but the switching frequency here, that can be 20 kilohertz or even higher. So the duration here talk about microsecond. Even the motor is rotating, that millisecond will be sometime. Supposing we know that constant in terms of motor rotation. So that we say, even though this is changing even though change the speed, but usually we don't change the speed within microsecond. Even the motor can change the speed within microsecond. We only change speed for every after 2 seconds if you don't want to do that. So that's why we can still assume that will be unchanged. So make the equation simple, easier to solve. So now then you can see that during the dt to d period dt, to D period, then this becomes negative. Negative means the current is now decreasing. Okay, dropping the current must be. Positive mean increase, negative mean decreasing. So that's what we can see here. Up to this, do you have any question? So the armature current will now decrease. This current, as I mentioned to you, is looping through the diode. So that now that if you want to see the diode current ID is equal to armature current, this you can see that in here. So firstly, this will be like this for this case. And then next, the current will looping in here, that will be for this case. Okay. We talked about that last time, so it's quite simple. I just show you the current waveform will be increasing and decreasing, which the equation will be like that. I think these two equations are quite straightforward, right? No complication. Okay, let's look at the next. Then, because we can see that the current increasing and decreasing, I like to see what kind of ripple appear in here. So ripple appear here, we need to be quite careful. Because when the motor increasing and decreasing, and when the motor becomes stable, we call it steady state, then the motor current supposedly not will increase to a large value, you're just stable, even though we can see some ripple there. So that's to say the DI going up, this amount of the ripple should equal to the amount of current you go down, so that you won't, just like primary and mounted. So that is to say, you won't do something like that, go up, and so that's a current increasing. We're not doing that. When the motor becomes stable, up and down should be the same. So that means the rising here should equal to the falling here. That's what I mean, under the stable. If they're not equal, you can imagine the motor current will keep increasing or keep decreasing. That is not the case we're looking for. So just tell you, when a motor in the standstill, when you start to change, probably initially the current will go up, and then, but once you go to stable speed, then you can see that the ripple will become more stable, up, down will become stable. So this is the stable. So this is so-called transient. Transient means it's not stable, it's still making changes, like the start up or braking. Or when we want to overtake a vehicle, then we are just changing the speed, then we call transient. But once the motor becomes stable, then we can see that the ripple also becomes stable. So this is the differential equation. If you want to just see the ripple, then we can see that the amount of variation here, which is delta, will be equal to also in this equal to this equation. Also this equation here. And the duration here, because we know this is the delta I, this is equal to dts, right? Just now we get that. The duration amount of time is dts. So the dt here, you can therefore change the dts. So if you know the period of the switching frequency, then you can put it in there. For instance, if the period is 1 millisecond and the d is 0.6, then that will be 0.6 millisecond. That's, yeah. And then similarly, we can also calculate the ripple during the fall. The decreasing ripple equal to this, because just this is d and this period is equal to 1 minus dts. The same kind of the concept. All right, you get that? So then you can see that these two delta, do you think they are different? Huh? Equal. Yeah, I just say they're equal. They are equal. So these two supposedly to be equal. And then if they're equal, then we can go to the next stage. So the amplitude are equal, but when going going up, one is going down, the summation equal to 0, right? So that's why when add them together equal to 0, then when we solve this equation, then we can see that many things can be cancelled out. Then eventually can get to the dV dc minus EA over RA equal to IA. So this equation look really much familiar with us. More look like the average voltage minus the back EMF divided by the RA resistance equal to the armature current. So the equation concept is the same as what we see in the previous lecture when the input motor voltage is pure DC. Okay. So that means you come to so complicated equation, we now come down to a simple operation, very simple operation. So you can think about that equation will be the DC voltage after the square wave, then its average become a duty ratio of for the input DC voltage. We just now mentioned about the average voltage to apply to the motor equal duty ratio multiplied by the VDC. So that's so-called the DC voltage here multiplied duty ratio will be our average voltage to the motor. Average voltage. Yes. And then just now the back EMF still unchanged. Because the switching frequency is so high frequency compared to omega is not compatible. So we can still consider within all the switching ripple there, the omega is not changed. It's still very much look like constant. Because you can see that this frequency used for 60 Hz, switching frequency 20 kHz. And 1,000 times different. So we need to change for 1,000 cycle, then the omega can change. So that's why you can still consider this more like constant. So that means you can therefore fit in using this equation, you can also work out about the omega. So then a few basic equations you can see from here. So again, the final equation want to ensure that will be average voltage of armature will be duty ratio multiplied by the input voltage. So this three equation is quite straightforward. I think everybody can memorize that. Mainly just to tell you, even though we are using square wave applied to a motor, the equation come out will be really similar to a previous equation under pure DC voltage. It just look like after the square wave, we just average the voltage. We use square wave to lower the voltage to average the voltage. That's all. So the concept is the same, very easy and simple to memorize. And even though the differential equation here also quite straightforward, I think you all can handle it. Okay, any question up to this point? So another thing we like to understand more about is so-called this steady state. Steady state, as I mentioned many times, when the motor, after we turn on, you eventually go to a stable speed. So we call it steady state. Then in this case, the motor speed look like constant. The current look like constant, doesn't change. So we call it steady state. But you can see that the ripple current, usually in our analysis, try to assume them to be small, IS. So the ripple, why the ripple should be small? Although we know that that's enough. The ripple, supposedly, we try to design the system to be small ripple. Anybody tell me why we like small ripple?
It's more stable.
Yeah, of course, stable, then we got less ripple. But what is the consequence? If we had large ripple or small ripple, how's the consequence to the motor, mainly about the motor?
I'm assuming efficiency.
Efficiency, yeah, and you can say that the ripple will cause you additional harmonic losses. Because for DC conductive loss will be DC loss. But when you have high frequency, we got additional loss, we got skip effect, so we got additional loss. But only here we still haven't considered that yet. The high frequency loss still are something we'd like to avoid, but that will be controllable. But anyway, when you see that the ripple here, because the current, armature current is proportional to the torque. So that means if that ripple current appears in the armature current, supposedly you can still see the torque at this kind of the variation, this ripple, which we don't quite like. You can see that if our motor is driving some really important robotic system or PCB system, or maybe it's kind of the fabrication system, we don't need any ripple voltage, ripple torque. Then affect the assembly line, maybe affecting the each vehicle, the robot. You don't see the robot just shaking the hand. Yeah, impossible. But however, so how are we going to decrease the ripple here? Make the ripple become small. What the principle? We know there's a ripple in the current. We know the current ripple will affecting the torque. We don't like the torque has ripple. What can we do? How do we improve that? That's some of the design requirement. Then the easy thing to do will be look into this equation, to the ripple like that. The ripple related to voltage, the DC voltage, right? DC voltage related to power level. Probably, of course, you say, no voltage. That may not be the case because we maybe high voltage to power the motor. The back EMF related to the speed, right? Usually, you can see that usually VDC and EA are really close to each other, only different by a little bit. And then we have voltage drop on the resistor, the winding. And then the mainly will be this three term probably controlled by the power level for the motor. High power level, then your RS will be smaller, the resistor may become smaller, and the higher power of the motor, then current will become larger, right? So probably these three terms are quite fixed. But one thing you can see there is the DTS, the TS. TS is the switching frequency here. That is the frequency we are talking about, right? So that to say that is the power electronic driver to your electronic circuitry. So if we use 1 kilohertz, then this will become 1 millisecond. But if you use 10 kilohertz, that will become 0.1 millisecond. So look at that equation. You can see that if you use T as 1 millisecond compared to 0.1 millisecond, we can decrease the ripple down to 10%. So in freely you can able to get high frequency, you can reduce the ripple. It's straightforward. Right? So that's why we use power electronic. As I mentioned to you, always we tend to use high frequency to reduce the ripple. So that means we use higher frequency. Then that means TS will decrease. And then the delta IA will therefore decrease. And then delta torque ripple will therefore decrease. So that's what we like to see the design system look like. So we always like to calculate the ripple. When we design it, then we need to know how much the ripple in the armature current. Then the input voltage, we do know about that. Then we also, the back EMF usually calculate from this equation, because under the stable environment, then the constant will be fixed, the flux will be fixed, the motor speed will be constant, more or less constant, unless we are changing the speed, we are overtaking a vehicle or something like that. So usually they are fixed. So that means all of them are fixed. Then we can measure the current, right? We can calculate current quite straightforwardly. Then we can, all these terms can calculate, and the delta we can also calculate quite easily. Although these current are changing in such a way, but the ripple is small, then when we calculate voltage drop on the resistor, then we're just using a DC current, IA, to calculate. That should be good enough. We don't need to say, oh, the current is now varying like triangular waveform, then we need to make this equation more complicated. But for this level, or for when we reach higher frequency, then IA usually assume them will be constant. Then you're still able to get the parameter for the ripple. So that's what my statement saying. Don't worry too much about ripple. We know the ripple going to be small. Then we can also use it to calculate IA anyway. So that means the current appear in the DC source. Now we like to see what's the DC side current. That means in here, we know the armature current is IA current. We have some ripple, right? But DC source will be like this. So when we turn on, armature current equal to input current. So that's why this waveform will be equal to this waveform. So now then you can see that this waveform exactly equal to this waveform. Yeah, because the current are going through this way, right? And then when we turn off this, the armature current still need to continue to flow, right? So this current will therefore appear as the diode current in here. So these two shapes are exactly the same. So that's to say the armature are either conducted by the transistor or the diode. So that means these two add together will be equal to this current. So that's what I'm trying to say here. So if the input current is that kind of the waveform, then this is an input current. If we want to see the average current from the DC source, from the battery, then how to calculate? You can see this is a triangle. This is a triangle. The average of the triangle equal to this one. IA. So this is the model like the average value for the armature current. And then the whole, because there's only a square wave, the whole thing will just look like this square, the average over the big ratio. So that means the input current in the battery or in the power source will just equal to this I current, and then we multiply by the duty ratio. So become this equation. Okay, do you get that? We always multiply duty ratio to get the average. So the input current, the input side current will be just equal to the average of the armature current. You can see here, we have been using a lot of the terminology average, duty ratio to average current. Square wave after the average, then you can see the current become more look like much lower value. How much lower is in the duty ratio to lower the current. So there's some implication why we need to use this method to lower the voltage, to calculate average voltage. One reason will be, you can see that you've got battery here. And then now it's taking the current in this kind of the waveform, right? If you want to find out the power from the battery, then we just need to use the voltage multiplied by the current. The battery voltage we know is DC fixed value, but when you multiply by the current, then it's getting complicated. We need to know what kind of current it is. Then later on, I can show you what we need to do to find the power rating or input power for the motor or for the battery. Then we just using the DC voltage for the battery and multiply for this current. That will be the input power from the battery or from the DC source. Because later on, you can see that will be a simple integration to prove that. So that's why we usually we will deal with that switching current waveform. But however is coming out from the battery, then you can just average the current multiplied by DC voltage. That also become our DC power coming out from the battery. In this few slides, we're going to show you how we do that. So that's why before we do that, then we'll show you the average current from the motor or from the transistor. You can use this simple field ratio to get the average. So let's see example to see some calculation, then you know better about how much we need to do that. So for instance, we have same waveform here. Now we have separate excited. We usually use separate excited because when we deal with the series component, then field current will be equal to armature current, will be really complicated. So we do something simple first. So now we are powered up by a DC-DC converter, which is this one. It's a very simple DC-DC converter. The input voltage will be 600, and the parameter will be the RA 0.05, the back EMF constant 3.818. Yeah, so the back EMF constant equal to K factor. We combine them together anyway. And then we try to use some controller to control the input current in the armature will be 250 amp. And the ratio for this DC to DC converter was 60%. And the motor inductance will be 0.6 millihenry. So for high power motor, you can see that the inductance usually are quite small. Although we are using the unit Henry, but we seldom see motor will be 6 Henry. We don't have that. Henry, just to tell you, is really large unit, really large. Most of motor you see every day, transformer, the inductance, we never have a few Henry. So if you see somebody at a paper, they say a few Henry is impossible, too large. So usually just a few really for most of the machine or motor transformer you see. So anyway, so the inductance here will be just 0.6 millihenry. For instance, the transformer you did in the lab, if you want to measure its inductance, I think you did that. I think the inductance really small, right? How much inductance did you measure? Did you remember? LRC meter, have you measured that? Have you done that experiment? Measure the inductance and put the air gap, and then to see the variation of the inductance? You're doing that. I think last week, have you finished it? You want to? If you cannot finish, you can go again to try again. Yeah. Although with the lab will be go then every 2 weeks, if you cannot finish it, you can only transform, you got plenty of components, you can come again this week to try again. Which one will finish that? You can see that when you put an air gap and not put an air gap, it changes the inductance. It changes the reluctance for the whole setup. It's quite nice to see that you can lift up the paper, then you can see the variation. If you want to get high grade, you can put a few more paper to change the air gap, and then to see the variation of the reluctance. And then you can see how the inductance being changed. If your inductance related to n squared over the reluctance. So that's another last part you can try. If you cannot finish last week, then you can go ahead this week to do it again. But anyway, coming to here, the motor inductance of all the inductance you see in most of literature and then pedicle transformer or motor usually that in the unit of millihenry. And the switching frequency here, they're using 5 kHz. So 5 kHz is quite a reasonable frequency for large motor. For some small motor, you may use 20 kHz, maybe 50 kHz. But for this kind of high power motor, 600 volts, then probably a few kHz of motor control system will be more suitable. So now then we are going to calculate the input power from the DC source. So remember just now we mentioned about the input power from this DC voltage multiplied by this current. This current comes from the average duty ratio and the armature current, right? Average. And so that's why just now I asked you to understand how to calculate power. We use average current to do that. And the impedance from the DC source, that's something strange. What's the DC impedance? DC impedance means if you got eye here, when you watch here, what kind of impedance you're able to see from the DC source. The DC source is just something you have supply voltage, and then you check how much current. So usually the measuring the resistance is the voltage divided by current. So for that DC source, there's some current coming out from here. So how much resistance on here, what you can measure with get that voltage, measure the current, and the ratio will be the impedance you can see. So that means the whole thing here look like a resistance. So that's how we calculate the input impedance. And then we are asked to calculate motor speed, the motor torque, back EMF, and the ripple torque. So the ripple torque are mainly come from the current. That's how I actually calculate ripple for the armature. So armature ripple multiplied by the torque constant, give you the ripple torque. When you check my notes about how we calculate, you want to spend 1 minute to think about how we calculate. I give you 1 minute to think how we calculate each part. Using your equation you learn, are you able to calculate them all? Not complicated, only with all the equations here are quite simple. We only just a few equations. Yes.
So for power, isn't it just power equals current times the DC source? Given current, I guess we have to make our voltage the average voltage.
You mean which part, the A part?
Yeah.
A part is DC voltage multiplied by the current. That's, and then because the current is not a pure DC current, it's a fluctuating current. So that's why previously we get the average first. The average multiplied by DC current, that will be the power. Just like when you measure power, you use a current meter to measure current, but that will be average current. But something I need to tell you will be getting more important. You know that when you measure current, it can be average current or RMS current. When you learn the electrical circuitry, there will be two terminology for the current. One is average current. Another term we call RMS current. What's the difference between them? Which one is used to measure power?
Using the I. Using the I.
Using the
I.
Yeah, the current is I, right? So IRMS or IM to measure the power.
RMS, right? Because I know it's zero. So it's like
What do you think? When you measure the power, then for the current to be measured, the RMS current or average current. Average current. They're all different ones. Talk about that. How the gentleman at the back? Average or RMS current to measure the power. I think you all learned that electrical circuitry. Have you studied how to measure power in the electrical circuit? You've done that, right? What did they say? V times I, yeah, V times I, and then after V is the V RMS or average, after I is the RMS or average. When do we use which? They never say that. So that's something that is also important concept when I teach the student what's the meaning of power, how to get the power, when we use average, when we use RMS. One thing will be important when you go to the lab, you use multimeter, you measure the current. The current usually with RMS current. But it's not all the case when we calculate the power, measure the power, we use RMS current. Only certain conditions use RMS. And I found that many students or even many professors they don't understand. So I have here, right? So when you do part A, then you will know. So let's go to part A first. The average voltage is equal VDC in the input side. That will be 0.6 pi 600, right? So that equation 5. But however, for DC power from the input side, so we firstly using the basic equation to do the calculation. So that means IDC, VDC integrate. So all the basic definition for power will be I times V dt to integrate that. And then let's see how the integral shall look like. So the input voltage from here There's a DC voltage, just like a battery. Of course, must be 600. Constant 600. So that means this term is a DC constant, 600. So that means when you conduct the integration here, so that means the power EC equal to this constant VDC, then you take it here. Okay? Because constant, we can put it in front of the integral, right? You get that? It's 600. From the back, this voltage is not changing. It's a fixed from the DC battery. So put it in here, and then you only need to integrate the current. Integrate this current. This current is square wave, pure square wave. When we integrate this current, that means we're going to get an average for this current, not the RMS. Right? But simple integrate, we did not put I square R to have a charge. So that means we only use 250 amp for the armature current. We control the armature current at 250, and then multiply its ratio. That's average. This integral is purely average. So when you measure the DC current on this condition in the lab, I ask you can measure the power in here. You make sure that your motor current measurement is using average current. Of course, you can calculate using the current 250 multiplied by 0.6, that is the average current. But your meter need to be using average meter. Do you get that? So don't use RMS, it's wrong. There's some condition we use RMS, but there's no coverage here in the electrical circuitry. Yeah. But if you check your looks again, you're able to know when we use RMS current, when we use average current. Under that condition, when we input a pure DC, we use average current. But in many cases, when we input an AC system, then we usually use RMS, but all depends on condition. Better thing will be to change that integral. The basic definition for the first integral I and B integral then with T, then that is the way how we use average when we use RMS. Not all the case we use RMS. In this case, we have to use average. You get that? So in here, then we have 600 volt constant DC from here, then the current multiplied by 0.6, then we get the average armature current here will be 60 kilowatt. So the power we get it from the DC source, or power for the average power for the motor will be equal to 60 kilowatt. And we also like to double check with the motor power, because here, this equation, we only calculate DC source power. And so this DC source power should equal to the whole motor power too. So to get the motor power for the motor equal to average, the IA current, armature current, with the voltage on here, right? The motor voltage. So the motor voltage here, again, we have 250 current. We assume the current to the motor are constant. The current for motor cannot be square wave. The current for motor must be a constant DC, more look like DC voltage. As I mentioned to you, the inductive current cannot disappear instantly. So that means the current for the motor, this IA will continue to flow with 250 amp, I think in the question, 250 amp here. When turn on, the motor current will conduct in here. When turn off, the motor current will loop in here. So the current only can become constant. Maybe it has some ripple, but it won't discontinuous. You get that one. But the motor voltage can be square wave. Just like we mentioned, we go on and off, of course, this one becomes square wave. So that means if you now then you calculate the motor power, then what we have here will be the motor current still 250 here. This is a constant, 250. And then when we integrate the motor voltage here, that will be equal to duty ratio average. Okay. So that means this expression here, the motor, so that means equal to integrate. Then the IA current you can put in the front, VDC, DT, yeah. So we average, so this is the, so this one is the motor voltage. I should use lowercase, I should lowercase. There's some typo here, should be, that should be, motor voltage, V in. So I said typo here should be V in for the motor voltage, right? Like that, yeah. I will change it later on. But anyway, the concept here, this is constant, which is 250 amp. This is mean the motor voltage. So when we average them will be 0.6 times 600. Okay, that's how we get to that. All right. So what we need to do here will be we will know which one is fixed and change parameter, which one is changing parameter. In my example here, the changing parameter uses square wave, it's just using duty ratio to average. So I just write it down carefully. I will update it later on. So the power equal to IA, and then with the motor voltage, it should be lower, should be like that. So this is the motor voltage here. Okay. It's an FFA. Any question up to this point? Now, after this lecture, is able to distinguish how to calculate AC power, DC power, and especially power, how we use average current, maybe average voltage to calculate power. So in DC input DC battery side, in here, the battery voltage or input voltage DC. So we integrate the current. The current is square wave. So in here, you can see that this current is square wave. So we use average. But in this equation here, this is constant. This is DC current, unchanged, right? So we only integrate the IA. So that means this equation, and therefore equal to IA, we can put in the front and we then integrate the V in dt. Okay. That's how we distinguish these two. The concept will be quite straightforward. You need to know which one is a constant, DC or unchanged parameter, which one is square wave parameter. The square wave parameter we usually using DC to do the job. Sorry, we usually using simple duty ratio to average it to get the average parameters. So obviously, the two methods we calculate, the motor power is 90 kilowatt and the input power also 90. They're supposed to be equal because the input battery provides 90 kW of power to the motor. So these two should be the same energy. So next thing to calculate will be the input impedance from the battery side, from the DC side. So firstly, to get the impedance will be DC voltage divided by the DC current. Then that's how we get the impedance. So the input current in here is, although it's square wave, we get its average value. So now again, it's duty ratio multiplied by 250 amp, the same as before with 150 amp. So this current appear in the battery side, in the DC side, is now become average to be 150 amp. So that means the denominator we use 150, and then the DC voltage is the battery or the DC source is 600 volt. So now the impedance is 4 ohm. So what it means here, if we view from here, you can see a 4 ohm in that side. So the DC source, you can imagine, you can only understand that look like 4 ohm for the whole motor drive plus the motor. So DC or input impedance also quite common. We usually tend to model something, try to understand the load requirement. We'll be using this kind of impedance. And then we try to calculate the voltage and current, get the ratio, then we can get the impedance in the input side. Then the speed, okay. So we get the equation. In the last week, this will be just the DC voltage, but now then we use average voltage. Average voltage minus the voltage drop on the resistance, and then divide by the torque constant. So we get up to 91 radian per second. 91 radian per second. So remember, equation is exactly the same as before. Instead of 600 volt, because we're using the transistor, we can therefore average the input voltage of the motor become only 60% of the 600 volt. So that's how we get this equation. So 91 radian per second, but usually we may not understand 91 radian per second. We use RPM, more common unit. So we just convert them into RMS. RMS is more real-life unit, but this is more SI unit scientific. So we can answer radian per second or RMS, both are good. And the next thing to the carry torque. So again, the torque constant here multiplied by IA current. So that will be equal to this one. We have not touched anything about ripple here yet. So we just assume the current is controlled to be 250 amp. We did not say anything about ripple, but we can calculate it later on if you like. And then the back EMF will be also the same torque constant and multiplied by omega m. So remember that we are using SI unit, so SI, that's a radian per second. We use 91 here. We don't use this one because that equation needs to be SI unit. So become 347 volt. Anybody can tell me 347 volt in the back EMF. So this motor, we're going to be 347 volt here. Input is 600. And current, you think 600 so large compared to 347? Because in the first lesson I mentioned to you, the input voltage compared to back EMF should be quite close to each other, only different by just a few percent. Why here would be such a big changes? So any number you can see here, you should ask yourself a question. Why is that? Then you can learn better.
The RPM's too low.
Say again, the RPM still
RPM's too low.
low? No, if you see if the DC voltage and the back EMF even by so large, all the voltage drop will go to the armature resistance RA. Then R is supposed to be really large. The current is supposed to be huge. It's 200 volt, 200 volt, 250 volt applied to the armature resistance, impossible. You burn the armature resistance. But it's not the case. The current only 250 amp, not that much. So what happened? Is there something we haven't thought about it? Why these two voltages different by so much? In the fast field example, usually they are very close to each other. What happened here? We see actually this 600 volt, this is 347. So we require a big difference. But both the voltage across here, the average voltage, this voltage sometimes 600, sometimes 0 volt. The average voltage appear here is 600 multiplied by 0.6, 360. So actual voltage here, average voltage only 360, not 600. So 360 compared to 347, they're okay, only about 5% go to the power loss in the RPM. That's very much reasonable. So why I say that, because for motor itself, the motor only see the square wave. The motor only understand the average voltage. They lump all two voltage, 600 together into their winding. Or you can see the winding current only current go up and down, go up and down, some ripple. So the use this current generate the torque. So motor itself, they don't care about instant voltage. They only care about the average voltage, the magnetize the motor. So that's to say the average voltage here compared to EMF should be quite close to each other. If they're two large different, we have problem, but now we have no problem because 360 volt here, 347 here is very good design. You get that? So that's really important concept. Although many students may ask, oh, 600 too large, you damage the motor. No, that's not the case. As long as the battery voltage will be reasonable to the motor, that will be good. Okay. Any question up to this point? Yes.
Know the average voltage.
Oh yeah. The depend on this transistor, this would become 600. We turn off the current looping in here, this becomes 0. So the motor voltage across here, sometimes 600, sometimes 0. So the duty ratio is 60%, 600, 40%, 0. The average will be 600 multiplied by 60%. So that is, we already done that. We already calculated in here the average armature voltage, the first line, DVDC here is 360. We done that already, but that didn't say too much. Make you think more carefully what it is. So that's a quite important concept. When we examine the motor, then we more favorable to look into the average voltage to the motor. The motor, but of course the peak voltage 600 volt is still important to the motor because that 600 volt will apply to the motor winding. If the motor winding will be only have 10 winding, for instance, then each winding will be 600 divided by 10. So this the winding, there will be 60 volt. So we need to make sure that the winding can able to stand for this 60 volt, the voltage spike or voltage rating. Sometimes between the winding, you burn because the insulation break down. So that means 600 volt is important for calculating the motor winding or the motor rating. Make sure that the winding is able to survive for high voltage spike. So that's the thing we need to consider. So we consider both. We consider the average voltage and also the peak voltage. Just to make sure the motor winding, the magnetic core, the insulation able to survive for that high voltage. Okay. Any question up to this point? So next we're going to calculate top, but we only have 2 minutes. So we think about that. So the first line here, you can see that the torque are given by this equation anyway. But IA, although we can see up and down, but we can assume then the ripple is small. So that means the torque is basically calculated from torque constant multiplied by current. So that means if we see a ripple in here, we can still see some ripple torque. But how we calculate ripple torque? We can use that equation. Because either rising or falling, that ripple in the rising and falling should be equal because they must balance. How much you go up, how much go down must be the same. So that we can use either one equation, rising equation or falling equation to calculate the ripple torque here. The ripple torque basically from the torque constant multiplied the ripple current. Ripple current are coming out from that equation. So that directly multiply the parameter into here, 600 volt minus the back EMF minus the resistance drop here, then we can get. So remember, the duty ratio is 60%. So that's how we get the ripple. So, and then how we get the TS. The switching frequency is 5 kilohertz. So that's why TS will be 0.2 millisecond. Yeah, I think we all know that. So put 0.2 millisecond here, we got 14.4 ampere. So 14.4 ampere put into the torque equation, we can get the ripple is 55 Newton meter. So 55 Newton meter look quite large to us, but if we try to get the compared to the total torque, it's not that large. The total torque we calculate is 954. So 954 is the total torque. So that means only about 5 point something percent. So usually for motor design, we prefer motor torque ripple to be something around 5 or less than 5% will be reasonable. Anything more than 10% can see some vibration. So of course, less than 2% even better. So these are just average, not really nice motor, still at 5.7% of the ripple. So that basically you can see that how we able to operate a motor. The important part will be how are you going to reduce the ripple. To reduce the ripple, I think I told you before, ripple are controlled by the ripple current. How we know the ripple current? We use higher frequency. High frequency, lower the period, the TS will be lower. So when we use higher frequency, if this go up, this will go down, then the ripple will go down, and then the top ripple will also go down. So that's this kind of the sequence, right? Go to here and go to here. So that's how we able to reduce the motor torque. Very important to design electric vehicle with the robot with the motor arm is shaking. Impossible. You can't do any motion. So we need to ensure that must be really, really small. The smaller it is, of course, more expensive because we need to invest high frequency. We need better chip, high frequency chip to control the motor, right? So that's the consequence. Any question? Yes?
We're having a 100% the ratio. Current ripple.
That's a really good question. If 100% we just fully turn on the transistor, we put in full voltage to the motor, then full DC to the motor, then we don't have anything happen, we don't have any ripple. But bear in mind, not all the motor we can able to turn on 100% fully, because we may overrate the motor. When you motor control, we usually using unilateral control to move the power, variable power, and then we have variable speed controls. For VSD, I think we learned VSD, variable speed joint. That is the same concept. VSD is quite an important control method. For all the motor drive, if you go out, you buy any inverter, you can see the term called VSD, variable speed drive. Variable speed drive. So that is using duty-based control is part of the VSD, which you did last semester for solar DC truck. Now we're looking at how we control the motor. Any other questions? No? Okay, we continue next week.